x square greater than 1 plus x, ln 1 plus x whole square x greater than 0. Now here we define a function fx equals to x square by 1 plus x minus ln 1 plus x whole square x greater than equal to 0. Now we consider that fx equals to gx minus hx, where gx equal to x square by 1 plus x and hx equals to ln 1 plus x whole square. For x greater than 0, gx is a differentiable function. Gx is a differentiable function. And hx being a square of logarithmic function is also differentiable. Hence, fx equals to gx minus hx is differentiable. For x greater than 0. Now we differentiate this fx, that is f dash x, we get first one u by v rule x plus 1 whole square. So x plus 1 ddx of x square is 2x minus x square into 1 minus twice ln 1 plus x by x plus 1. Now this one further simplification will get 2x square minus x square, that is x square plus 2x. We get here 2x square plus 2x by x plus 1 whole square minus x plus 1 into ln x plus 1. This gives us x square plus 2x whole divided by x plus 1 whole square x greater than 0. Now here, since we can't conclude anything that is greater than 0 or less than 0, so what we'll do here, you see. Now this one we defined as px. Let px equals to x square plus 2x minus 2 into x plus 1 into ln x plus 1 x greater than equal to 0. Now it is a sum of quadratic polynomial and a product of linear and logarithm function, so px must be differentiable function. So px is a differentiable function. Px is a differentiable function. Now we find p dash x, which is 2x plus 2 minus 2 into x plus 1 into 1 by x plus 1 plus ln x plus 1. This gives us 2x plus 2 minus 2 minus twice ln x plus 1. 2 common, x minus ln x plus 1. Equation 1. Now this part x minus ln 1 plus x. This is also greater than 0. This is always greater than 0 for x greater than 0, but that we have to show here. So here we define ux equals to x minus ln x plus 1, x greater than equal to 0. Ux is a differentiable function because of the difference of linear and a logarithmic function. So ux is differentiable function. So u dash x equals to 1 minus 1 by x plus 1. So x by x plus 1 greater than 0 as x greater than 0. Therefore, ux is strictly increasing for all x greater than 0. Ux is continuous at x equal to 0. This implies ux is strictly increasing for all x greater than equal to 0. And this implies ux greater than u0, which is 0. And this implies x greater than ln x plus 1. Now, from 1 and 2, we can say p dash x greater than 0. From 1 and 2, we conclude p dash x greater than 0. This implies px is strictly increasing. Px is strictly increasing for all x greater than 0. Px is continuous at x equal to 0. Therefore, Px is strictly increasing for all x greater than equal to 0. This implies Px greater than P0, which is 0. And this implies the Px which we had, that is x squared plus 2x minus x squared plus 2x minus 2 into x plus 1 into ln x plus 1 greater than 0. This implies x squared plus 2x minus 2 into x plus 1 into ln x plus 1 whole divided by x plus 1 whole square greater than 0 when x greater than 0, because this is a positive number. And this implies f dash x greater than 0 when x greater than 0. Therefore, fx is strictly increasing for all x greater than 0 as fx is continuous at x equal to 0. This implies fx is strictly increasing for all x greater than equal to 0. And this implies fx greater than f of 0, which is 0. And this implies x square greater than 1 plus x into ln 1 plus x whole square when x greater than 0. That is the proof. One plus x ln x plus under root of x square plus 1 greater than root over of 1 plus x square x greater than 0. We define a function fx equals to 1 plus x ln x plus root over of x square plus 1 minus root over of x square plus 1 for x greater than equal to 0. Now fx is a differential function. So as fx is a differentiable function, for x greater than 0, therefore f dash x equals to x into 1 by x plus root over of x square plus 1 into 1 plus x by root over of x square plus 1 plus ln x plus under root of x square plus 1 minus x by root over of x square plus 1. On further simplification, we can understand that here, if we simplify what we get here x by root over of 1 plus x square minus x by root over of 1 plus x square plus ln x plus root over of x square plus 1. This gives us ln x plus root over of x square plus 1. Now here x is greater than 0. Now when x is greater than 0, x square plus 1 is greater than 1. That is what we mean to say. As x greater than 0, x square greater than 0, this implies x square plus 1 definitely greater than 1. So from this only root over of x square plus 1 will be greater than 1. Now if we add a positive number to this, so that will be definitely greater than 1 only. Now if we see the logarithmic function graph, this is y, this is y, it is x, this is x prime, this is y prime. So what do you observe from here? This is 1 comma 0. When x is greater than 1, the output which we get are positive. This is a graph of y equal to ln x. So hence we can conclude that ln x plus root over of x square plus 1 is greater than 0 when x greater than 0. Now this implies f dash x greater than 0 when x greater than 0. And this implies fx is strictly increasing for all x greater than 0. Now fx is continuous at x equal to 0. This implies fx is strictly increasing for all x greater than equal to 0. This implies f of x greater than f of 0, which is 0. And this implies 1 plus x ln x plus root over of x square plus 1 greater than under root of 1 plus x square when x greater than 0, which is the required proof. X greater than 0 less than pi by 2. Part 1. Sin x less than x less than tan x. We'll take here two functions. First of all, all right, let us consider function fx equal to tan x minus x for x greater than equal to 0. We consider including 0. That is, I am considering this function for greater than equal to 0 also. Now they have told us for x greater than 0, but I have taken here whenever I applying any property, I will be taking only for greater than 0. Now, if we differentiate this is a differential function for x greater than 0 less than pi by 2 is equal to 0 also. We also the function, but at the end point we cannot say about the differentiability. So when we say about the differentiability, we will say only the open interval. So right, as y equal to tan x and y equal to x, both are differentiable for all x belongs to 0, pi by 2. Therefore, fx is differentiable for x belongs to 0, pi by 2. Now we differentiate f dash x. That is sec square x minus 1. Now for all x belongs to 0, pi by 2, sec square x greater than 1. This implies sec square x minus 1 greater than 0. This implies f dash x greater than 0. So fx is strictly increasing function. For all x belongs to 0, infinity. Now, as fx is continuous at x equal to 0, therefore fx is strictly increasing for all x belongs to 0, infinity. Therefore, fx is greater than f of 0. Because why we have to do that? Because it's shifting from 0 to infinity. So now we can write f of x greater than f of 0. And this gives us tan x minus x greater than 0. And this gives us tan x greater than x. We'll consider here gx equals to x minus sin x, y equal to x, and y equal to sin x, both differentiable function. So gx is differentiable. So g dash x we find 1 minus cos x greater than 0 for all x belongs to 0, pi by 2. So gx is strictly increasing. Gx is strictly increasing for all x belongs to 0, pi by 2. Gx is continuous at x equal to 0. Therefore, gx is strictly increasing for all x belongs to 0, pi by 2. Therefore, gx greater than g0. And this implies x minus sin x greater than 0. X greater than sin x. Now on combining, 1 and 2, we get sin x less than tan x. Here you prove sin x greater than x minus x cubed by 3 factorial. We consider fx equals to sin x minus x plus x cubed by 3 factorial. You can think this one as sin x minus x cubed by 3 factorial. You can think this one as gx minus hx, where gx equal to sin x and hx equal to x minus x cubed by 3 factorial. Sin x is a differential function, is a polynomial function. H is a polynomial function. So gx and hx both are differential. Both are differential function. So fx is differential. Fx is differential for all x greater than 0. Now we differentiate this and we get cos x minus 1 plus x square by 30. Now if we simplify this, cos x, we know the expansion. 1 minus x square by 2 factorial plus x to the power of 4 by 4 factorial minus x to the power 6 by 6 factorial and so on. Minus 1 plus x square by 2 factorial. And that gives us x to the power of 4 by 4 factorial minus x to the power 6 by 6 factorial and so on. Now, this whole thing is definitely greater than 0 for x greater than 0. Therefore, f dash x greater than 0 when x greater than 0. So, fx is strictly increasing. Fx is strictly increasing for all x belongs to 0, infinity. As fx is continuous, at x equal to 0, therefore fx is strictly increasing for all x belongs to 0, infinity. This implies f of x greater than f of 0. And this implies sin x greater than x minus x cubed by 3 factorial. Because f of 0 is 0. We can simplify this one. That is sin x minus x cubed by 3 factorial greater than 0. Since for all x greater than 0, sin x greater than x minus x square by 3 factorial. Therefore, for all x belongs to 0, pi by 2, sin x greater than cos x greater than 1 minus x square by 2 factorial. Is less than 0. So here we consider a function fx equal to cos x minus 1 plus x square by 2 factorial. Now, this is a differential function. This is a differential function. We can think this one as gx minus 8x, where gx equal to cos x and x is equals to x square by 2 factorial minus 1. So if we think as x square plus 2 factorial minus 1, then we can make it plus, or we can do another thing. We can write it as 1 minus x square by 2 factorial. Now since cos x and these are both are differential functions, that is gx and hx. Here gx and hx both differential functions. both differentiable function. As y equal to cos x and y equal to 1 minus x square by 2 factorial, both differential, because one is cos function and is quadratic following. So both are differential. Now f of x, from that we find f plus x. So minus sin x plus x minus sin x plus x. Now when x is greater than 0, when x is greater than 0, we know x is greater than sin x. When x is greater than 0, we can see that from the graph also. That's why this is x prime origin, x, y. This is y equal to sin x. You can see this is pi, this is 2. So here you can understand that the line y equal to x is above the graph y equal to sin x. So you utilize that concept and we write that in 0. Therefore, fx is strictly increasing. Fx is strictly increasing function for all x belongs to 0, infinity. Now, fx is continuous. Fx is continuous at x equal to 0. Now, if it's continuous at x equal to 0, because you can say that f of 0 and limitation to 0, f of x will give us the same value, so it's continuous at x equal to 0. Now we can say that fx is strictly increasing. Fx is strictly increasing for all x belongs to 0, infinity. So this implies f of x greater than f of 0. Now f of 0 is 0 here. So what we can say that cos x greater than 1 minus x square by 2. Since for all x belongs to 0, infinity, cos x greater than 1 minus x square by 2 factorial. Therefore, for all x belongs to 0, pi by 2, cos x greater than 1 minus x square by 2 factorial.